So thank you for having me to give this talk. So the title is, as mentioned before, on quantifying the error in multi-objective stochastic optimization. And so we'll break down what that means as we go. Given that much of the talk is going to be on multi-objective optimization, and I've sort of assumed that many of you have not seen that before. So we're going to spend a couple of slides in the beginning going over that, but definitely ask questions during that part, because if you still have lingering questions about what is multi-objective optimization, then it'll be hard to follow the rest of the talk. So I just wanted to say that up front. And this is joint work with Burla Ondes, who's my PhD student in the School of Industrial Engineering at Purdue, and also with Raghu Pasupathy, who's in the Department of Statistics at Purdue. Okay, so let's review briefly single objective optimization. So usually what happens when we have one objective in a model that we want to, say, minimize cost for some system, and I've just drawn a quadratic function here. So if your cost as a function of some inputs, here we have two inputs, x1 and x2. If your cost is quadratic function of these inputs, then it'll look something like this graph that I've shown here on the left side. And usually in such a model, we want to find the minimum. So the minimizer and also the minimum, and the minimizer will be called x star, usually in an optimization context. And what's important to note here is in a single objective context, we can see the input variables and output variables are on the same graph. So we see the x1, x2, and then we have, so that's the decision space, and then we have the objective space is coming up in a third dimension. But if we rotate this view in our minds and we look from the top down so that the cost is coming right out of the page at us, right out of your computer, these are the contours of this quadratic function. So I'll ask you to mentally rotate the picture and look down at it, and you'll see these circular contours, and the x star will be in the middle. So now I'm going to add an objective to this problem. So we have cost we want to minimize, but say that we also have some environmental cost. And so we care about the actual monetary cost and the environmental cost. So now imagine we have two of these quadratic functions, and the second one looks a lot like the first one, but it's just moved over a little bit. And so we have this top view in the decision space, where we have the contours of the cost objective and the contours of the environmental objective. And in multi-objective optimization, we want to minimize these together. So we want to look at all the points where if we move somewhere in the decision space, so say we move from cost over here, I'm assuming you can see my mouse, we move over here to negative 2, 2, then we've done worse on cost and environment. But if we move along this efficient set, we cannot do any better on one of the objectives without sacrificing on the other one. And so when we have multi-objective optimization, we want to identify the entire set of efficient points, where if we try to improve on one, it's going to force us to do worse on the other one. And what's also something to kind of wrap your mind around in multi-objective optimization is that it's very hard to get this link picture. So before we had the decision space, and then we had the objective space, and you can very clearly see the mapping between these. Often in multi-objective optimization, we have to separate the decision space from the objective space. So I've plotted the objective space on the right side. So we have cost is on the x-axis, and the environmental cost is on the y-axis. And then these points are plotted xy coordinates from over here on the left-hand side. So in the decision space, imagine there is a rectangle here at the end of the axes, and we have just discretized a bunch of points in that space. and then they map over to here. So these corners that stick up like this are the edges of this rectangle. And when we look at this map from the decision space into the objective space, we can see that the efficient set here is going to map to points in what's called the Pareto set. So the Pareto set is a set of all points such that they're non-dominated by any other points in the objective space and mapped by coming from into the decisions from the decision space to the objective space. So everybody in this space maps to a point that is behind the Pareto front. So we don't want to choose a system design in our decision space that's going to map to a point where we could have done better on both objectives if we'd tried harder. We'd really like to choose something that is right in the Pareto front. And what you'll notice is the benefit of doing this is that you can assess the trade-off between the monetary cost and the environmental cost. So you can see that your monetary cost will be low here, but the environmental cost is very high, and you can reduce the environmental cost by 10 units without having too much extra cost in monetary cost. So maybe this point, the point that maps here, which is somewhere along the efficient set, would be much better than the point that maps here. So this is the minimum on cost, which is the origin. So this point maps here. The environmental cost is, the minimum is going to map over to this point. So the decision maker can then look at this trade-off and say, well, we clearly don't want to pick something that has such a big environmental cost when we can just pay maybe a little extra monetary cost and we get something that does much better. So this is the benefit of multi-objective optimization. Many times in actual applications, real-world applications, people have multiple objectives in mind. They even have things that are not incorporated into the model, that when they see this trade-off, then they can make decisions based on how that trade-off is looking to them and what they care about. So I'll pause here for questions. We are going to go through some examples next. Yes, so so this is all deterministic. So you have a deterministic model, quadratic, two objectives, and we're going to move into what does it mean to make this a stochastic model next. So any questions about this picture or anything we've done so far? And I'll wait just a few, maybe 30 seconds, and if there are no questions, I'll just go ahead. So now if we have some uncertainty, there is a question. How do we deal with the trade-off between the two objective functions? So this is a good point. So what an algorithm that's trying to solve this problem will do, and the thing that we are going to care about, is characterizing the entire Pareto front and characterizing the entire efficient set. And then that will be input to the decision-making process. So if there's some board of people that are trying to make a decision, the mathematical analyst will come in and say, this is what your Pareto front looks like, this is what your efficient set looks like, and then the person in the room can look at it and assess how they want to proceed based on the information now that they have. So something else becomes clear, this example is only two objectives. If we had many, if we had 10 objectives, I couldn't show you this plot. So there's a whole area about reducing the number of objectives, displaying when it's many objectives. And sometimes if the Pareto front is very large, you can get the Pareto front first and then try to optimize over that. And there's an entire bit of literature on that as well. But our goal for today is going to be always to get the entire Pareto front, or at least a characterization of it. If this thing is continuous, in finite time with finite machines, we won't be able to get the whole thing. So that was a great question. Okay, so this is all well and good, but many times we have to model uncertainty because we don't actually know what the cost is going to be. We have some uncertain prices, we have uncertain weather, so we don't actually know what our environmental cost or our monetary cost will be. So we're going to express these functions as a function of both the decision variable and a random variable. So capital Y is going to be a random variable such that the probability Y is in its support is 1. And then how do we incorporate this kind of uncertainty into an optimization problem? How should we do it? How can we account for the fact that the function values are random for each little x decision variable that we want to see? So we're going to focus on an approach that I'm going to call the expected value approach, which means that we're going to consider the multi-objective stochastic optimization problem, where we have a vector of objectives, f1 of x all the way up to fd of x, where we're taking the expected value of these random functions, and they're vector valued. There are other ways to do this. One of the other ways is called robust multi-objective optimization, where instead of looking at the expected value or trying to do well on average, you're instead going to optimize for, say, the worst case scenario. So there's other work on this, but we're going to focus on the expected value approach. It turns out that this approach has many applications, and we'll talk about 2 of them in the coming slides. The robust approach also has many applications. So these are just 2 sides, different ways to model a problem that has uncertainty inside of it. So one of the most classic multi-objective problems there is the Markowitz portfolio optimization problem. So suppose that you have a decision vector, which denotes the proportion of your assets that you want to invest in each of Q available assets. And the random variable is the random returns for each asset. So I can put $5 in asset 1, $8 in asset 2, and so on. But then each of these assets is going to, at the end of the year, give me some random return that I don't know in advance. But of course, I have to make my decision now. I can't wait and see the return and then allocate my investment. I have to do it before I can see. But I have historical data on these investments, so I have a sense of what the expected return might be. So I want to maximize my expected return, which means I want to minimize my negative expected return to make it a minimization problem. But then I also care about my risk. So I care about the variance of my return. And I don't want my return to be bouncing all over the place. I might like to be into assets that they're going to pay off with some certainty. And so this is formulated by Harry Markowitz in, I believe, 1955, very famously. He later won a Nobel Prize. And last time I checked, he is still alive, I believe. I forget his affiliation. He has some affiliation in Chicago, which is very close to Purdue. So this is the problem that we have in terms of our portfolio allocation. And the key point here is even though we're taking an expected value approach, we are accounting for some measure of risk. So we can, in this approach, we can encompass some loss functions that you put inside to account for the risk. So I've just plotted a 4-asset portfolio optimization problem from Boyd and Vandenberg's book. So we have, this is a simplex here saying that you can only allocate assets that you have, basically. And the efficient set turns out to be this line that kind of goes through the space, mapping over to the objective space. And so we have a Pareto front here that indicates how risky versus the return each one of these allocations will be. And so then you, the person who is investing, can look at these trade-off and say, well, you know, I'm only comfortable with so much risk, so I want to have a portfolio based on this trade-off. I'm going to maybe reduce my risk a little bit, and I know that my return probably won't be as good in expectation. So that's the idea here. Another example which is one that will be with us for a little while throughout the talk, is bijective convex quadratic stochastic optimization, but really I've formulated as a bijective least squares problem. So if we want to fit a linear model, we have a parameter x, so the model is linear in the parameters. And suppose that we have two sources of information. So we have one source of information might be some real-world experiment that we ran, or we have real-world data on a system, but we can also get extra information about that system through a laboratory experiment. And so we may be able to have two separate linear models, one that accounts for the real-world data and one that accounts for our laboratory data. But really, we want to have one model. We just want to use these two sources to try to make our model better. So R1, Q1 is going to be an input-output pair for the model, such that R is the response and Q is a random vector of covariates. R2, Q2 is the analogous input-output random variables, but they have this auxiliary information. So this makes the model sort of a gray box type of model. And we want to fit one model or one set of parameters using both of the sources of data. And we can assess then, using this bijective optimization problem, we can see what is the trade-off in choosing different parameter values. So I've plotted an example true problem. Before we had some quadratics where the level sets look like circles. These are also quadratics, quadratic objective functions, but I've plotted them where their level sets are ellipses. So these lines are remember we're looking top down. These are the contour lines of the quadratics for the second objective, and then the contour lines for the quadratic from the first objective. And this is in the decision space. You can see then that the efficient set is going to bend. And this is a set of all points such that we cannot improve on both objectives at the same time. Then this efficient set maps over into the objective space. And remember, these are the parameter values, and then this is measuring the error in our linear model fit. And so we'd like that error to be as small as possible because we have data, we're going to have residuals, so there's going to be some error, but we want it to be as good as we can get it, given our two sources of information. And so we have one place where the first model fits the best and one place where the second model fits the best. But we may want to look at this and calibrate our model based on the knowledge of the expert who has access to the system and knows really well about it. So the key question we're going to come back to this as well, but the key question you've probably picked up on is, we don't know these values, right? When we do least squares, we have data only. So these objectives cannot be observed directly. We don't know the expected value. That's the whole point. We're modeling that they're coming from some distribution, and we want to assess these values where we can only observe them with error from data or from a simulation model, some stochastic oracle. And so in this case, we have a lot of questions, right? How do we solve a problem like this when we have this kind of error? How do we quantify that error? And it turns out the development for theory methods and algorithms for solving these continuous MOSO problems, it's really in its infancy. There's not a whole lot of work. It's related to several other areas. So there's a relatively high level of development for continuous single objective stochastic optimization. So just one objective, like on the first slide, but we can only observe it with error. There's a relatively high level of development. Oops. Yep. Okay. It worked. So there's a relatively high level of development for continuous deterministic multi-objective optimization. In fact, this field is older than single objective stochastic optimization. This is probably now, I'm going to say, just a guess, from the 50s and 60s. So almost maybe 50 to 70 years old, somewhere in there. Multi-objective optimization is over 100 years old. So there's quite a lot of development here. Apart from the very popular metaheuristics that come up there's little development for continuous multi-objective stochastic optimization. And when I say little development, I mean in terms of theory, what kind of convergence rates can we get? Central limit theorems? Do we have algorithms that converge with probability 1 to the true efficient set as things become dense, as we're able to sample more and more? And we really don't have much information here in terms of development. There are a few things here that I've listed, but it's very small compared to the individual development of single objective stochastic optimization and multi-objective optimization separately. So this is going to be a talk in 2 parts. So the first part, we're going to talk about, given a real-world MOSO problem with an unknown solution, so something like our mean variance formulation portfolio allocation problem, or our bijective least squares problem, how do we evaluate the quality of an estimated solution and its image? And so we're going to talk about how we might build confidence regions on the answers to such problems. And that's going to be the first part of the talk. The second part of the talk is going to be, given a test bed of problems with a known solution, how do we assess the algorithm's performance? So this is kind of, the first part is saying, you have a problem in the real world and you want to solve it. Let's say by hook or crook you solve it. How do you know how your uncertainty is behaving in that case? Can we visualize it? Can we say with 95% confidence or something like that, something about where the solution would lie? In the second part, we're going to say, okay, well now I suppose I have that, but I want to sample more. What is my performance metric, first of all, for assessing my solution quality? And then how do I go about sampling more? How do I determine how much I need to sample? What are the rates of convergence? So in the work that I do, the convergence rates are sort of bread and butter. Like certain things converge as 1 over square root n, other things converge exponentially fast. If I argue, and I'm going to argue to you, that we should use Hausdorff distance to measure the quality of the solution in a multi-objective simulation optimization context, then what kinds of upper bounds can we place on this theoretical performance? How much computing power do we need to even be able to solve such a problem? And how do I allocate that sample, that computing power, going forward? So I'm going to argue to you that Hausdorff distance is right now one of the better metrics that I can think of for using. And then we're going to be able to bound that Hausdorff distance because it's a metric. We can use the triangle inequality. We'll get a discretization error plus a selection error. And we're going to spend quite a bit of time trying to get the discretization error term in the second half of the talk. So let me pause here again for questions, if there's anything, before we head forward into the meat of the talk. So we're essentially going to talk all about the error and how do we deal with it. Okay, so let's go back to this bijective least squares example. And we're going to suppose now that we only have data. And we want to quantify the uncertainty in the solution. So we're going to obtain IID copies of this vector. Remember, R is the response and Q is the covariate. And we're going to get a bunch of copies of these. We're going to stack them into a matrix. The response will be R tilde, and the covariate matrix will be Q tilde. And then we're going to construct what's called the sample path problem. To an optimizer, this is the problem where you estimate things with the average. Remember, our goal is to minimize an expected value, so we're estimating here the problem that we cannot observe directly. So now we have 1 over n, sum over all my observations of this penalty term for deviation. And I have that for each data set, the one that's in the real world and the one in the lab. This is the optimizer's mentality formulation. From statistics, you'll probably recognize this is the classical least squares. And notice that if we're minimizing, the 1 over n constant does not affect the optimal value. So it does not affect the optimal solution. It does affect the optimal value, but we're looking for the x anyway. So here we have the F bar. We'll recognize this as a least squares problem for the first data set and then the second data set. And the solution to this problem, we're going to call it E hat n, which is an estimator of the efficient set. And it has image P hat n, which is an estimator of P. And so we're dealing with data, right? We have the estimators E hat n and P hat n, they're uncertain. Can we obtain a 1 minus alpha confidence region on the efficient set and on the Pareto set? And so I just took a pen on an iPad and said, okay, it might look something like this in the decision space. It might look like something, these green areas. We'd like to be able to plot something like that to say, when I have my estimated efficient set, where do I think the region where the true one might lie would be? So this leads us to a problem statement. So we want to create confidence regions for the MOSO context. So we're going to pose the following problem statement. We're given a significance level alpha. This is familiar, 0.05. The significance level is common. We're given a stochastic oracle that for any decision variable x, sample size n, IID y1 to yn, is going to return the random variables fx, y1 to yn, and they all have common mean little f. And we have data. So we have, for some non-empty subset of the feasible set, which we observe data, we're able to get these data points. Now we want to find a set that is a subset of the decision space and a set that is a subset of the objective space, such that in the limit, the efficient set is a subset of that set with probability 1 minus alpha, and the same in the decision space. So we're going to look at what can we say in an asymptotic way, asymptotically valid confidence intervals, or confidence regions. So a few methods exist to construct confidence regions on the efficient and Pareto sets. There's actually only one method we know of in the literature, that is by Vogel in, I believe, 2017. And these confidence regions are valid for each n, which, as the author notes, makes them understandably conservative. So they are not asymptotically valid. For whatever n you have, they are valid. Bootstrap and subsampling are also viable candidates for doing this. What we're going to do is look for something that directly exploits the structure in a MOSO problem. So these two methods are quite general. And we're going to, in doing this exploitation of structure, we're going to hope that it leads us to smaller confidence regions than if we did not exploit such structure. And there's a question, do we have assumptions on the distribution of uncertain variables? Not yet. We will have some probably very basic regularity assumptions, but not yet. And certainly we're not going to assume that the number of scenarios is finite. So it can be continuous support. But it's gonna be standard assumptions like the second moment is finite, this kind of thing. Or possibly exponential decay in the tails for the estimator. Okay, so for a moment, we're going to analogize what we're used to, the familiar confidence interval, up into the MOSO context. So we're going to see if we can say, well, this is what William Gossett did. can we do something that mirrors what he does? So recall Gosset's confidence interval on the mean mu. If we have data x1, x2 up to xn that are IID normal with mean mu and variance sigma squared, then we construct something that's called the root. X bar minus mu divided by sigma hat n divided by square root n. And the key thing that Gosset showed is that this is t distributed. So one of the first key steps is figuring out what is your root, what is the statistic that you are going to determine its distribution, and then determining that distribution. And so we know this is true, but it holds regardless of what the value of mu is. So remember, we don't know the distribution for the random variable, but for any mu, right, this is just a standardizing way to standardize the mean. And so when we subtract off the mean here, we don't actually have to know it in order to say that the statistic is t distributed. So essentially, we go through the math, we construct a valid confidence interval as x bar plus or minus the t critical value, sigma hat over root n. And the key point being that even though we use mu in the root to determine the value for the distribution of the root, then the mu does not actually appear anywhere here when we construct the final confidence interval. And all of this theory assumes that the x1 to xn are IID normal, but recall that usually we're going to invoke a central limit theorem to get the normality of x bar, right? So it's very common that this will become then an asymptotically valid confidence interval. Otherwise, you'll have to say it's an approximate 1 minus alpha confidence interval. So I'm trying to help you reach back in your memory and see that we use this sort of asymptotic validity all the time. And it allows us to do nice things like say that the root is t distributed and create these kind of confidence intervals. And the central limit theorem is something that kicks in quickly. Some limit theorems, they take a while to kick in, but others kick in very fast for not much data. And so when we have that situation and we have enough data, we'd like to use the limit to help us create a smaller interval. So now we want to try to analogize Gosset's method. So a naive attempt is going to construct a root that looks something like this thing on the right. So we have an estimator for the efficient set. We might like to subtract off the true efficient set. And then we need to scale by some kind of standard error parameter in the denominator. But there's really three key challenges to doing this. First thing to notice is as written, the e hat n minus e, it does not make sense. E hat n and e might be totally different sets. They may have different cardinalities. They may really, there's no mapping between them inherent in this expression. So we're going to address this challenge directly as a first matter because we want to create a root. So we have to address this idea that we need to subtract sets. So let's suppose that we resolve the first question and we construct a root. Then we want to know, what does it converge to? Can we get an analog of a t distribution or, what kind of central limit theorem, in quotes, might we be able to create that will help us have an asymptotically valid confidence region in this context? So we'll show that our version of the root goes through a specific Gaussian process, and it's our central limit theorem, so to speak. And then the third challenge is that we don't know this standard error object. We don't know sigma. And if we replace sigma by sigma hat, where somehow we are able to estimate something like that, then what does the root converge to? And we have a conjecture that asserts the weak limit is neither Gaussian nor Student's t, but it's going to be a functional of the Brownian motion. So let's start with challenge one, this subtraction issue. How do we subtract sets? So the way that we're going to do this is using scalarization. We're calling it also parameterization, really the same thing if you're familiar with scalarization. So we're going to take this multi-objective problem and transform the objectives. We're going to let the parameterization be called phi. And so we have this problem where we have a scalarization parameter s. It's in some set, script s, of possible parameters. And we're going to minimize phi of s comma f of x. Don't worry about this notation. The key point is, for the rest of the talk, it's sufficient to just think about the linear weighted sum scalarization. So this is arguably the simplest one. What we're going to do is take each objective and multiply it by a weight, and then sum across the weighted objectives. And when we do this, we get a one single objective problem. Then if we change the weights to something else, we get a different single objective problem with a different solution. And so under certain conditions, as you change those weights, if you have convexity and some other properties, you will get the entire efficient or Pareto set as you solve for every s. So if we apply the same scalarization, linear weighted sum, for example, to the true function value, which we don't know, and to the f bar in, which is our estimated value, then we get a mapping between the true efficient set and the estimated one. Then we can subtract. So if the functions are strictly convex and we have the linear weighted sum example, then given a scalarization parameter in the possible set of parameters, we know that the solution to each scalarized problem is unique, and we can write the sets E and P, which are the efficient and Pareto sets, and their estimators, as E is the collection of all the solutions across the scalarization parameters, and P is the image of that, the collection of the images of the efficient points. And we can do exactly the same thing for the estimated values. So now we can consider what I'm going to call a scaled error field. So we get a stochastic process where we take for each scalarization parameter, we're going to solve the sample path problem, then we subtract off the true value, and we can scale that and look at it as a stochastic process, which is just a collection of random variables. We're going to look at that over the entire set for scalarization. We do this in the decision space and in the objective space. So now this is kind of starting to look like a root, right? This is where we have the thing that we care about minus its mean, and we have a scalarizing, excuse me, a scaling parameter, and then we're looking at the whole collection as a stochastic process. So now we can come to our so-called central limit theorem. Here we have some list of assumptions, IID copies of Y, feasible set, things need to be compact, the functions need to be strictly convex. I'll just remind you, this is a first level, we have some assumptions, it's a first level result. We'd ideally be able to relax these in the future, but so we'll go ahead and assume the simple case to get the theory nailed down straight away. So then we have that our scaled error field converges in distribution to a mean zero Gaussian process. And if f is Frechet differentiable, we have an analogous result in the objective space. Notice here that we've sort of skipped out the whole question of a variance parameter or a scalarizing variance. That is embedded in the right-hand side. So we have this result, but then we need to estimate some covariance object. And so ideally, when we do this, right, we cannot scalarize at every point. Realistically, on a computer, we're going to have to pick discrete values. So we're going to pick R sub n points in the scalarization set and solve the problems for those values across the efficient or Pareto set. So we'll get R sub n points in the sets. And then we're going to do what's called batching to get a covariance object. So if we use all the data at once, we just get a single estimator of the efficient set. So we're not going to go over all the notation here, but E hat in sub Rn is that discretized estimator using all of the data, right? So if I use all the data, I just get one estimator E hat, but it's discretized at my chosen scalarization points. Now I'm stacking this as a big vector. So it's going to be the dimension in the decision space times the number of scalarization values. And then I'm going to subtract off the true one. And now I have to hit that with an estimated covariance object. And so this thing is going to be a QRN by QRN matrix that is estimating the covariance across these values. And then I have a square root n on the outside. And we're able to show then, as a conjecture, we think we can show that this converges in distribution to a quantity for which we can characterize the critical values. Remember, back when we were doing confidence intervals with William Gossett, he showed the distribution as t, and then that's how you get your t1 minus alpha n critical value. Here, we're going to use this distribution that we can characterize to get the critical value. And so once we have this result, which is analog of Gossett's result, then we can create a confidence region by looking at all of the vectors in this QRN space that are within certain distance of the estimated grand total. So remember, the batching is, if we only have one E hat in Rn, we need, in order to get a variance object on that, we need a bunch of these, right? So the way that we get a bunch of these is by taking the data, and I'm going to segment it into batches as we go through. And for each batch, I'm going to calculate an estimated efficient set. And then I'm going to see how they vary across the batches. That's how I'm going to get my covariance estimator here. So when we do that, we're able to calculate confidence regions in this way for the critical value that's defined using this distribution. So if all of that is just a little bit overwhelmed, I have some preliminary results for an example in the biobjective least squares. So I created an example for which we have a multivariate normal random vector. And these are all the mu and sigma values where we get the mean and variances for our response and covariate values. And then I took 500 samples. I discretized at the level of 0.02. Whenever we do linear weighted sum, we can use it on the unit simplex. Since we just have two objectives, I'm just going to take my scalarization parameters from 0 to 1. And then this means that I have 51 problems that I'm going to solve for the scalarization. And then for the batching, I took batches of 100 with a displacement 1. And the batch size is then going to be 401. So going all the way down the data set to get my covariance object. And if we do this, remember this was the example from before. It's the same picture I showed you. And we try to draw the confidence region based on the conjecture. We get something that looks like this on the right-hand side. So we get an estimated Pareto set, and then we get the uncertainty cloud around it in gray. And if you're able to zoom in here, it's hard to see, but I've plotted these little circles are the scalarizations. So the 0.2 scalarization will be one point, the 0.4 scalarization will be another one. And they're very close together as we go down, but then they get a little bit farther apart here in the bottom. And you'll notice that I've gridded this evenly. It's important to see that when we grid evenly in the scalarization, it doesn't mean that the values we get in our Pareto set or estimated Pareto set are going to look even. And this is a common problem that people in multi-objective optimization worry about. There's a lot of work in that space about how to get the even spread. I did something naive. just to show you that it's an issue. But we need to be careful about how we pick those scalarizations, because ideally we would have the points going throughout, evenly throughout the Pareto set. So as we're sampling, we're quite sure that this region, the gray region, will cover the true Pareto set certain percent of the time. So we've done things quite, preliminarily. We're just beginning on this work, and there's a lot of open questions and extensions. So how can we scalarize evenly in the objective space and in the decision space? Because we're wanting to create these in both spaces. How do we accommodate non-convex objective functions? We've done linear weighted sum, and we require strict convexity at the moment to make sure that we get a correct mapping. So how do we handle this when we don't have this strict convexity? And more importantly, how can we use this information toward creating adaptive sampling algorithms? If you plot your Pareto set and say that you really want to narrow this part of the region, then you might want to sample there more and see if you can get more data in that area. So how can we do that when we have to spend in samples per point, for example, in a Monte Carlo simulation context? So that concludes the first half of the talk. And I see that we're headed on about 50 minutes in. So we may not make it through the second half, but I'll pause here for questions again before we head into the second part. I might blitz you through the second part. Okay, so let's move over EVPI and VSS. Would you be able to spell out the acronyms? Expected value of Pareto information, is that correct? Value of stochastic solution. Yes, so these kinds of, my understanding of like expected value, it tends to arise more in a Bayesian context, or when you have a meta model, like a Kriging meta model. There's also the concept of value of stochastic solution. I see this come up in like two-stage programming. We are assuming very general structure in the multi-objective stochastic optimization field in general. So my background is Monte Carlo simulation modeling, where you don't assume any structure. We have some results where we need convexity, but ideally I'd like to go to a place where we don't have any particular structure. And so we might see, so I'm not sure value of stochastic solution apart from a two-stage. I'm not familiar with that at the moment. The expected value of Pareto information reminds me of the expected value of information that's usually seen in the Bayesian Kriging context. And that is another way to go. It is not the same as a confidence interval. The inference will not be the same. So usually in a Bayesian context, the inference is conditional on your data, whereas we're trying to get inference that is not conditional on the data. So yes, it is the answer, but to a slightly different question than what we're asking. Okay, so let's head into the second part. So we have sort of this idea of confidence regions, quantifying the uncertainty. You want to solve a problem in the real world, but you have no idea how good your solution is or what kind of error there might be in it. This gives you a way to put some confidence around it, so to speak. for lack of a better word. Now we want to move into what kind of bounds can we get on performance? What kind of performance measures should we be using? What kind of bounds can we get on those performance measures? How fast might our algorithm converge? How hard do we need to work to solve this problem? How much more do we need to sample to get a nice solution? So we're broadly going to take the approach that we know the solution for a little while. Our bounds will not depend on knowing the solution in the end, but we're going to for now assume that we know it so we can compare to some true value. And I'm going to argue to you that we should be using Hausdorff distance for specific reasons. There may be other things we can use. There's I think over 100 performance indicators in the multi-objective optimization literature. So it's by all means not the only one, but it's the one that has popped up for me as being the most important right now. And then the question becomes, what kind of upper bounds can we place on the theoretical performance of a MOSO algorithm? And we're going to do a bound of discretization error plus selection error. Okay, so in this part of the talk, we're going to have a very general solution context. What we're going to do is we're going to discretize the decision space. So we're going to sample some finite set of M points, and then we're going to estimate the objective function values at those M points. So we're going to, this is the original problem. Then we're going to say, okay, we're going to look at M points in the decision space. That's going to be feasible sub M, script X sub M. And then at each of those points, we're going to get an F hat estimator by just taking a sample average. So E hat sub M of N is going to be the efficient set estimated with stochastic error on the discretized space. EM is the efficient set with discretization error only. So if we could observe it for real, remember we're pretending we have the solution right in our hand. So we can observe the true values at those M points. And then we have PM is going to be the image of the true solution for the discretized problem. So the key notation here is E hat is estimated discretized, E hat M of N, and then these are just discretized. So we want to see how well our algorithm is doing. So we've got some M points, and we've got an estimated efficient set on those M points after we've taken samples and estimated the objective function values. And so we have this idea of the true image of E hat M of N. So we discretized and sampled, we estimated what we think is our efficient set, and now we're looking at what are the actual values for those points in the objective space. And this is a key difference from actual multi-objective optimization when everything is deterministic. Usually, those indicators do not account for the possibility that you would return dominated points, because for the most part, you will not return dominated points. If there's no error, no stochastic error, you can just look and see that one point dominates another, so you'll get rid of it. That's not the case when we have stochastic objectives. We may very well have points in this set that are truly dominated. And so that's the key point. We need to account for the fact that we might actually have points truly dominated. And when we go to check an algorithm that is returning dominated points with one that isn't, we'd like to penalize that algorithm that's returning all these extra points. So popular metrics, hypervolume difference, this is shaded in gray. This gray shading does not change whether these points are here or not. And in a multi-objective context that's deterministic, by and large, they won't be there. So this is not a critique of multi-objective optimization at all. They are doing exactly what makes sense. The critique is when we move into the stochastic setting, I'm not sure it still makes sense. I feel like these points should matter. The coverage error is in blue. That's the distance from the Pareto set to this true values in the estimated set. Here again, this coverage error is not accounting for the extra points in here. And of course, in the MOSO context, both performance measures are random. So contrast this with the Hausdorff distance. The Hausdorff distance is going to check how far, across these points that I'm returning, how far can they be from the Pareto front in truth. So now it matters that we have returned this extra dominated point. So that is my reasoning for moving forward with Hausdorff distance, because we're saying, hey, if you return extra points, that's no good. We're gonna penalize you. You can imagine there are other ways to penalize, right? You could take, we have this hypervolume difference. You could take the back end of the hypervolume, where if you're a point that dominates another point, you throw it out and then calculate the hypervolume difference. That's another way to go, potentially future work. So we're going to focus on this Hausdorff distance, which is the max of the coverage error, and then this other distance where we look across the true values of the estimated efficient set in the objective space and look for the nearest point in the Pareto set and take the max across those values. So we're going to penalize the algorithmic riffraff and consider this Hausdorff distance. Notice that this is a random, because we have random variables in here, then this whole quantity is random. So we're going to need to deal with quantiles or an expected value. This thing has a distribution. So this is just recalling our setup. We have m points, and we're sampling at each one some amount. We're going to measure the quality of the selected point set, the feasible set x sub m, by its dispersion t. So the key point here is t is the smallest value such that the cue balls around the points cover the entire feasible set. And because we've chosen the points that we're going to sample at, t is known to us. So if we grid a q-dimensional unit hypercube, it's square root q divided by 2 floor m to the 1 over q. And so we know t as a function of the dimension of the space and also the number of points. This is for gridding. We can also get approximations for when you do uniform Monte Carlo sampling. So we're going to measure this as the quality of the discretization. And now we want to know what is an upper bound on the Hausdorff distance as a function of t and n. So we know that Hausdorff distance is a metric, so we can use the triangle inequality to split this into a discretization error, which is fixed. This is the Hausdorff distance between p and pm, and a selection error, which is random. And so much of the rest of the talk, to the extent that we have time, I might just blitz you through it so that we can get to questions, much of the talk is focused on getting this discretization error. I was very surprised not to find it in the literature of multi-objective optimization. And then we know this selection error happens to come from a different set of literature. So we're going to end up with bounds, but the focus mostly is on getting this term. There, I've highlighted it. Yes, that is the focus. So how do we get an upper bound on this deterministic discretization error? I was, again, surprised not to find it in the literature. We do know for the coverage error, the distance from E to EM, that is less than or equal to t, and the distance in the objective space is less than or equal to h of t, where h of t is the distance from the image of the worst point in a t radius ball around the efficient set to the Pareto set. So if you don't absorb h of t right away, just think of h of t as a way to get results that happen in the decision space into the objective space. We're going to work completely in the decision space, and then this h of t is going to translate it over into the objective space. So we get an upper bound that is based on the coverage error. We know how that converges. It converges as order t. So we can say the Hausdorff distance between E and EM is less than or equal to the max of T. And then we have to get this right. This is the other side that we had the orange line, but mapped in the decision space, right? So we want the distance from EM to E. This is the orange line in the objective space. So how do we get this term? Essentially, what we need to do is find an upper bound by solving an optimization problem where we rearrange the points we're sampling, but we do it in such a way that we preserve T, so the value of T is the same. We can add points, is okay, but we want to maximize this distance from EM to E. That will give us an upper bound. So we're going to rearrange all the points in the decision space until we get as far away as we can get. And then if we can solve that problem or get an upper bound on it, then we can use h of t to translate the bound from the decision space to the objective space. This turns out to be quite a hard problem. I did not realize when we started. So the key point is that we're only able right now to do this for bijective convex quadratic programs with positive definite Hessians. So we're back to the simple quadratic case. In this case, we're able to get bounds. It's an open question to get them in general or for Lipschitz. We have the coverage error bound is for all Lipschitz, but the other side of the Hausdorff, we don't know for Lipschitz objective functions. So we have this assumption that everything is quadratic and the feasible set, of course, is compact. Everything is pretty. And under this assumption, when we have quadratics, we can show that h of t is big OT. So anything that we do in the decision space is basically going to translate the same rate into the objective space. Now for our result, we can show that for any configuration of points that you sample in this decision space, the discretization that we have here, then we have an upper bound basically showing that it's big O square root t. And this is important because it's actually quite a bit slower than the coverage error, which is order t. There is some resistance in the multi-objective optimization community to using Hausdorff distance because it's considered conservative. And this quantifies in what rate is it conservative. So coverage error is order t, Hausdorff distance is order square root t, at least when we have convex quadratic objectives in the bijective case. So this is a general result. We have it also that the Hausdorff distance between P and PM is order square root t in the objective space. So we have results in both spaces. And we have a special result in the case where we have spherical level sets. So this kappa star is the maximum condition number across both objectives. So if the condition number maximum is 1, that means we just have circles like we had on that first slide, all quadratics with circular level sets. We can show that we have a least upper bound in the length of the efficient set. So we have this result, and then also, for any positive definite Hessians, we get the big O square root t result. So I'm going to stop there. I have lots more intuition on the proof for that result. And we have an example that shows that the least upper bound, that the bound is a least upper bound when we have spherical level sets. So key point here, we can come back to this bound and plug in when we have bijective convex quadratic that we have big O square root t for the discretization error. The selection error is random, and we can actually get this a bound on this selection error from an entirely different area of literature called multi-objective ranking and selection. And so we broadly know that from that literature, the probability our Hausdorff distance is bigger than some value epsilon, it's going to decay exponentially fast in the sample size n. So now we have big O square root t, and then we have an exponential fast in n. Now we can start to say, okay, how much more should you sample? How much more points should you look at? How much more should you sample at each point? These are the kinds of things we'd like to be able to say. And we can also say, how hard is it? This is, as a function of t and as a function of n to solve this problem. Remember that t and m are basically dependent on each other, so that one will determine the other in some sense. So open questions and extensions. Can we obtain an upper bound of the discretization error for 3 or more objectives? We've only done 2 objectives. When you have 3 objectives, even in the quadratic case, your efficient set goes from a line to a triangle. So now your optimization problem is going to be more complex because you need to optimize also over the possible efficient sets that you might see. So that's a complication we have looked at, but we don't have an answer yet. Can we obtain an upper bound on the discretization error that holds for all Lipschitz continuous objective functions? And then how can we use these bounds to design algorithms? So to determine how to select m and n when we're solving a problem in a naive way. I feel like when we're stepping into new problems, trying to solve ever harder problems, we should try solving it the naive way first and get theory for that naive way. That will form the basis of less naive methods. And many people, they might just like to solve it the naive way. They have lots of computing power, so they're going to do it that way, but they still want to be efficient. They don't want to, be inefficient just for fun. But not especially fun to be inefficient. Okay, so concluding remarks, we've discussed methods to quantify the error when solving MOSO problems, both when the solution is unknown in the form of confidence regions, and when the solution is known, Hausdorff distance. And we've been able to get bounds that really hold across a wide variety of solution methods, regardless of the solution actually being known. In both contexts, they provide valuable information for analysis in future algorithmic design, but much work remains. There's so many little things to pick off and work on here to extend the results and provide additional problem contexts. So thank you. I have a ton of references, I think 4 slides of references. So they will be there for you, assuming that you're able to access the PDF.